We are now ready to dive into the specifics of the statistical methodologies used in sampling distribution. A basic idea is to learn about the concept of sampling error. This brings us to the question, what is sampling error? In concise terms, it is the difference between what is observed based on sample data evidence and the reality. In other words, if we take the sample mean and we also have the population mean, and we take the difference between these two quantities, that will constitute your sampling error. To illustrate, take the first example. We're told that the population mean is 125 because this question says a population has a mean of 125. So that would be the population mean. I can make a note of that here. The mean is 25 based on the population. However, if we choose a random sample of 8 items from the population, it results in the following sampled values. This is the sample values. And the question before us is, what is the sampling error for the sample? Note something. Every formula you have for a quantity is like a recipe. So the sampling error in this case is the sample mean. So you need the sample mean, and you also need the population mean. So on my recipe, I need two ingredients, the sample mean and the population mean. I have the population mean already. I only need to first find the sample mean. So I'm going to pause off on this. So I'm going to say be right back. And I need to go to the store to get X bar, the sample mean. Now the sample mean would mean I need 103 plus 123 plus 99. I will continue all the way. Let's clean this up a little bit. I will continue all the way. I will add up all of these numbers, 99, 107, as far as 100, then 99, all divided by 8, since there are 1, 2, 3, 4, 5, 6, 7, 8 numbers. So this will be equal to, if I sum up all of these numbers and I divide by 8, I will have 106.5. This is the estimated mean or the sample mean based on the sample data. So now I can be right back to my sampling error. So my sampling error, I can shorten that as SE. This will be equal to X bar minus the population mean, 106.5 minus 125, and on my calculator, I got negative 18.5. So there are a few facts to note. If my sampling error is negative 18.5, it must mean that the sample mean was smaller than the population mean. In reality, this is what is unknown. In this case, this is what is known based on what sample data we collected. And from what I can see, if I'm using my sample mean to guess my population mean, the negative value here means I am underestimating the population mean of actual 125 to be 106.5. So I am underestimating it by a value of 18.5. With that said, let's see another example. We're told to assume that the following represents a population of values. So these are population values. And then question A, if a random sample of n equals 10 items includes the following values, that is, these are sample values, I am expected to compute the sampling error for the sample mean. Okay, based on what we have done earlier, we recall the formula. The sampling error is the sample mean computed from the sample values minus the population mean computed from the population values. So first I need to get each of the ingredients. I need the sample mean and I need the population mean. To get the first, which is the sample mean, this is the sample mean, I will go to the sample values. I would add up all of the data values from the first to the very last, and I'll divide by how many values do I have. This will be equal to 18. So now I have the sample mean. Then next, I'll proceed to the population mean. That will require me to add up all the population data values, 10, 14, as far as 6 and 35. And divide by how many values do I have here? If you count, I have 24. And that will give me 22.125. Now I have recipe 1. I have the first ingredient on my recipe, and I have the second ingredient on my recipe. So I can throw them into the cooking pot or the formula. So sampling error will be equal to 18 minus 22.125, and that is negative 4.125. Again, since this is a negative number, it means my estimate, my sample mean, was lesser than the actual population mean. With that said, we proceed to question B. In question B, we are told that for a sample of size n equals 6, compute the range for the possible sampling error. Take note of the difference between question A and question B. In question A, we only want to compute just the sampling error for the sample mean. In question B, however, we would like to compute the range for the possible sampling error. To compute a range, it means I'm going to need to start from one value to another value. So there is going to be a lower value and the upper value. How would we do this? Let's begin. Step 1 would be to look at the entire data set, the population of data values. I am going to find the 6 smallest sample values. I'm going to find the 6 largest sample values. I think a good way to start that would be to sort all data values to begin with. So anytime you want to compute the range of the possible sampling error, you want to sort all data values first. So how would I do that? I have this data set already in Excel. So I'm going to go into Excel, and here is the highlighted data set in the population. To sort, simply go to sort and filter. So click on sort and filter, sort from smallest to largest. Click on and just choose continue with the current selection. Excel will ask you if you want to take more data values. Just ignore that and say just continue with only the numbers I have currently selected and sort. And you can see that it goes from the smallest 6 to 35. Now we continue. Step 2 would be find sampling error based on the 6 smallest sample values. How do we do that? We are going to find the sampling error based on the smallest 6 values. So I'm going to call this sampling error of 6 smallest values. Remember, sampling error is always the sample mean minus the population mean. So it will be the sample mean of the 6 smallest sample values minus the population mean. How will I get the sample mean of the 6 smallest values? Excel will help me with that. I'll go back to Excel. I will choose the 6 smallest values. And how do I know I've selected 6 here? If you look down here, you'll see there's a count here, number of selected cells that contain data. I've collected the 6 smallest values, and the average automatically is 8.667. So I have that value. So I'm going to take that here. So I have 8.667 minus the population mean. Earlier, we got the population mean. It was 22.125. So I'm going to take that back here, 22.125. So with that said, I can take away this parenthesis. This is equal to negative 13.458. Then we continue to step 3. In the same way, or in the same manner, we found the sampling error based on the 6 smallest sample values. In step 3, we're going to find the sampling error based on the 6 largest sample values. So to find the sampling error based on the 6 largest sample values, I'm going to write standard error based on the largest 6 sample values. That will be the sample mean of the 6 largest values minus the overall population mean. To do that, again, I'll go back to Excel. This time, I'm going to select from the bottom. So I'm going to go all the way up, and I'm going to count until I get the 6 smallest values. So I can see my count is 6, and the average is 33.167. So I'll take that back to my workbook. 33.167, the average of the 6 largest values minus the population mean, which is 22.125 that we got earlier. So with that said, we have the average of the 6 smallest values to be, the sampling error based on the 6 largest values to be 11.042. Okay, so for step 4, we are ready to state our final answer. And that answer is that the range of possible sampling error, is from the least value, negative 13.458, to 11.042. Then we advance to question C. In question C, we have a very similar question to question B, except for the sample sizes. So we're only changing the sample size from 6 to 12. So we're going to follow similar steps as what we did in part B. We don't need to write it out all in full. So step 1 is sort the data values, which we have done earlier. Remember, in Excel, we already have the data values sorted. Then step 2 is to find sampling error for the 12, this time 12 smallest values. So how would I do that? Average of the 12 smallest values minus the population mean. This will be equal to, let's go and find this average of the 12 smallest values. So I am going to highlight and select the 12 smallest values here. So I have my count is 12, and the average is 12.917 approximately. So this is 12.917 minus 22.125 again. And that will give me negative 9.208. Then for step 3, I'm going to take the sampling error for the 12 largest values. That will be average of the 12 smallest values minus the overall population mean. That will be equal to, going back to Excel, I will pick the 12 smallest values. So I have 12 of them, and I have the average is 31.3333. Okay, so that will be 31.333 minus 22.125. This is equal to positive 9.208. And so my step 4 is to state the answer. And that will be that the range of possible sampling error is from negative 9.208 to positive 9.208. Now, it's time to step back and look at something. When the sample size was n equals 6, the range of the sampling error was from negative 13 let me look at it on a scale, negative 13.458 to positive 11.042. However, when the sample size increased from n equals 6 to n equals 12, the range of the sampling error went from negative 9.208 to positive 9.208. So one thing is clear. What do you think is the effect of a larger sample size on the sampling error? Well, it appears that as the sample size increases, the error due to sampling tends to decrease, because we can see that the interval or the range here is shorter. So we make a simple statement here that the larger the sample size, the smaller the size of the sampling error that we make when estimating the unknown population mean. This is very important quantity to note. The sampling error is simply the difference between your guess or your estimate of an unknown quantity and the actual value of that unknown quantity. We see that to increase the power of our precision, we can increase the sample size, and that can help. So we take one last example in this regard, and this is an applied problem. This says that to help in the solicitation of contributions, a foundation considered hiring a consulting firm. The firm claims that the mean contribution from families who contribute after receiving a specially prepared letter would be $16. So what that means is that based on this interest, which is the mean contribution from families who contribute after receiving a specially prepared letter, in general, or the population mean, is assumed to be 16. So before hiring the firm, the foundation decides to send out the letter and request what? Materials. So they received the 30 contributions shown below. Let's assume that this data reflect a random sample of the population of contributions that would be received. Compute the sampling error based on the claim made by the consulting firm. The claim made by the consulting firm was that in general, the average or the population mean is 16. Whereas this is the sample data values or sample contributions collected by this firm. So what will be the sampling error? Based on what we have learned so far, this will be the sample mean, x bar, minus the population mean, which is the general assumed mean. This will be equal to, we need to add up all of these data values and divide by how many data values to get the average. We can do that in Excel. So we have all of the data values. I can highlight all of them. So there are 30 of them, and the average is 16.133. So going back, this is 16.133 minus the actual or the guessed population mean by this foundation, or the suggested mean, which is 16, and this gives us 0.133. This is a positive sampling error, which means in a sense we are overestimating by 0.133. So what do you think? Do you think this consulting firm is doing a good job, or did they give us a very reasonable guess of 16? I would say so, because this is not so much. This is not so much a difference between what it really is and what the guess or the value you got from your sample. So, question B. In statistics, nothing is exactly what perfect. And so we want to comment on any issues you have with the assumption that the data represents what? A random sample. Well, here it is. Here is certain. When you make that assumption and you have no way to verify or validate your assumption, we have to state that as a caveat in our results. So here we go. There is no way to verify that the data represents a random sample from the population. This is because we do not know, something is missing there, we do not know if the people that contributed were randomly selected or were a random selection of possible contributors. We continue the question. Does the calculation of the sampling error matter if the sample is a random sample or not? Discuss. Let's write that down too. To answer the second part, we note that the formula for computing sampling error is the sample mean minus the population mean. Neither the sample mean nor the population mean depends on the randomness of the sample. So as a result, the sampling error of x bar, the sample mean, minus the population mean, does not derive or depend on the randomness of the sample member selection as well. So that's just something to note whenever we use the formula for computing sampling error. With that said, we have concluded on the idea of sampling error. We will see more as to how sampling error is a fundamental idea when we talk about sampling distributions.